But these basically type of eigenvector centrality is not suitable for directed graphs. So if we have a graph that is directed, we basically don't want to use this for that. And there's a good reason for that. So there are multiple challenges. If you think about basically a directed graph, it mostly doesn't have a symmetric adjacency matrix in general. It can have, but it generally doesn't have. So if you want to write the eigenvector equation for that, what happens is that you will have two sets of eigenvectors and eigenvalues. You will have a left eigenvector and eigenvalue and right eigenvalue and eigenvectors. So then which one of these should we choose? The idea is that, generally speaking, based off of your application, but generally speaking, the importance is for the incoming basically edges. So for example, let's say that a website, anyone can make a website and just randomly link all the websites in the world, and then it will have a lot of high a lot of basically outgoing edges. But let's say that we have, or even as someone that cites, you can write a paper and cite everyone in the world, and you will have a lot of outgoing edges. But that won't really add anything to your importance. In some special cases, for example, if you wrote a review paper, but most likely it doesn't show any importance of your own paper. So it is a good measure to just look at the incoming edges. And if we do that, we will sum over rows of the adjacency matrix. And what happens is that we will end up with the right eigenvalue and eigenvectors. Okay, let's do that. We have a directed graph, and we selected right leading eigenvector as our vector of centrality. So let's look at this problem. We have this graph. It has 5 nodes, and it is a directed graph. Node V1 has 3 outgoing edges, but has no incoming edges. So it basically doesn't have any importance. Its centrality should be 0, right? Based off of the previous formulation. You might say that, okay, it's fair because it doesn't have any basically incoming edges, so it is fair that it's 0. Okay, let's move forward. We have node 2, which has 1 incoming edge and 2 outgoing edges. So this one should have some importance. But the problem is that it is getting all its importance from its incoming edge from V1. So this guy has 0 importance. So this, although it has 1 incoming edge, its importance is going to be 0. So we can actually look at this graph and see every node in this graph is getting its importance from node V1. Because node V2 is getting it from V1, and V4 is getting it from V2 and V1. So again, it's going to be 0. Then V3 is getting it from V2 0, and V5 with 3 in basically degrees is going to have 0 importance or eigenvector centrality. So this can't really be the case. And one example is the citation network that I mentioned. In the scenario that people don't cite each other, what happens is basically I just published a paper, for example, not really, but assume that I did. And I have cited, for example, 5 people, and no one has cited me. So those 5 people won't get any importance. And this will go until the beginning of the time, whoever basically first wrote a paper that was cited. So if I would want to follow the idea with eigenvector centrality, no paper, essentially no publication has any importance. In order to remedy that, there's a method called Katz centrality, and it essentially associates some degree of importance to each node just by existence. So we rewrite the equation from previous page, basically previous method, eigenvector centrality, and we add a beta at the end of this, right? So we rewrite this in matrix form. where one basically here is just a vector of ones. And we basically rearrange this, so we have C only on one side, and this is what you get as the formulation for Katz centrality. Now we go back to our the graph that we studied, and we see that now, although this guy has a very the smallest importance, this guy is getting something from all others, and you see that their importance is proportional to the number of in degrees have. These have 0, the lowest importance. These have each 1 in degree, so these are higher than this. And this basically this guy is more than these 3, and this guy has the highest centrality. So now let's consider the problem that we have a set of web pages, and we want to order them based off of their importance. So we can use this basically type of the idea from graphs. We can assume that web is a graph and hyperlinks are just edges that connect one node to the other node. And so, for example, this is a graph from Notre Dame. What happens now is that we can select one of these measures of centrality. And so this is a directed graph. We saw that Katz centrality is a good idea. And what happens now is that we try to use Katz centrality to order these nodes based off of their importance. So let's use that. So let's look at this graph again. We had this node V5 with the highest importance among these nodes, right? So let's assume that there are some web pages and Amazon is in between them. And Amazon is, by any measure, Amazon is a very important website. It has been linked by many people. So let's say that this V5 is Amazon.com. Now let's say that I have a store and I have a web page for that store. It's selling some stuff and Amazon has linked me. So based off of this link from Amazon, I'm going to get the importance that Amazon has. So I'm also as important as Amazon. But that's not the only website that Amazon is linking. Amazon is linking to a ton of manufacturers that have a single web page that is, may or may not have any information other than their address somewhere in the world. So each of those will get some measure of centrality, basically the centrality of Amazon, and everyone is going to be a very important, high on the list of important websites. But that's not going to be true. If we want to look at web pages, it's not a fair measure to say everyone that was linked by Amazon is high in centrality. So a remedy for that is to say that, okay, we need to dilute this centrality that is propagating from being inherited from the node that basically points at the basically each of those small websites. So we can see the idea here. So let's say that we have node V1. Its importance, let's say that is C1, and it has 2 outgoing edges. So the importance of V1 is going to be divided by 2, and each edge will transmit C1 over 2 importance to the next node, the node that basically points to. We have V2, which has 3 outgoing edges, and C2 over 3 is the amount of importance that V3 gets. So the importance of V3, C3 is going to be C1 over 2 plus C2 over 3. And V3 itself is pointing at 2 other points, so its importance is going to be divided by 2, C3 over 2, and so on and so forth in every, essentially, node in that graph. Now we can write this using index notation. We can write this as our centrality is proportional to the sum over all the neighbors the importance of basically all the neighbors that are in neighbors, so the ones that are directing at you, divided by the degree of that node that is pointing at you. Again, we can get rid of this by noting that the in degrees are shown with the rows of the adjacency matrix for the directed graph. And what's going to happen is that we are left with this adjacency matrix element in between these. Now, there's a case that a node can have zero essentially edges that are pointing at anything. And that's going to make this equation be 0 over 0, because there's already no connection between I and j, because j doesn't have any odd degrees, and it doesn't have an odd degree. So both of these terms are going to be 0. So we set that in order to have a well-defined equation. We set that by convention to 1. And that's still going to have no effect, because in fact, any term that you put there, even not 1, any number that you put, it's going to be the same, because if j has no odd degrees, element ij is going to be 0, because j is not pointing to anyone, so it's not pointing to I as well. So this term is going to be 0, and it's not going to have any effect on the centrality of node I. Again, like the Katz centrality, we have the same problem that if some node does not have an importance, it's basically what will happen is in some scenarios is that no one will get any importance. So like Katz centrality, we add some, by basically definition, we add some free importance to every node in the graph at the beginning. We set beta equal to 1. It is, some measure of importance that I'm giving everyone for free. So it's not important what I'm putting. I just want to get rid of it in the rearranged formulation. I'm going to end up with this relation here. So this A D minus 1 is usually shown with P or M, and they call it a stochastic adjacency matrix. So it is a left stochastic matrix, meaning that its columns are summing to 1. It is like, so each basically is column you look at, it looks like a probability. And this measure now, the C is called a rank vector, which basically ranks web pages by their importance. And this method is called PageRank, and is basically the base method that Google uses for their web page essentially ranking. And this page comes from Larry Page, which essentially worked on this during his PhD. All right. So in the measures that we studied so far, we looked at the ideas that followed matrix representations, but there are also two others that are based on path. So one is called closeness centrality, which essentially looks at how close one node is to any other node in the graph. So for this, we defined previously what the shortest path in the graph means that how basically the shortest number of edges that you need to traverse to get from one node to the other node. And this closeness centrality is looking at the mean or average length of the closest paths from each node to every other node in that graph. So we write it this way. We say that it is so it is average, so 1 over the total number of the nodes that we have. And it's sum over all the nodes in the graph that have a path to node I. But the problem with this is that if a node has short path, basically a lot of short paths from the node we can basically find to every other node in the graph, that means that that node is central, but this mean of paths is going to be a low number. But we want to, usually when you should talk about centrality, we want the more central nodes have a higher centrality. So what people usually use is the inverse of this term. So they just write 1 over this average value, and they call it closeness centrality. So you can think about it as if you have a member in a friendship group that is basically has shortest distances to everyone in that group, his ideas, for example, will propagate faster in between those group of friends. All right, another term that we basically will see is betweenness centrality. Betweenness centrality looks at the idea that how between of different nodes one node is. So you can think about it as, let's say that we're in Western US 200 years ago, for example, and or 150. So, and people are just using horses and stuff to send messages. If you're sitting in a town and people are, let's say that people from different towns are sending messages to each other at the same rate. And if you sit at some town, you will see that, messages come and go through your town, and your town is a node, and the connections between towns are representing edges here. So let's say that if you want to send one letter from a city to another one, you select the shortest distance between them. You don't want to go around the country. You say that, okay. And in all those times, now there are optimization methods, and you see your Amazon parcel is going around the country before getting to your home. But, let's say that people select the shortest path to send their basically envelopes, and you sit in a town, and you see that horses come and go through your town. There are messages coming and going through your town. If the town is sitting in between a lot of nodes, a lot of cities, it will see a lot of traffic going through that town. If your town is just a remote town that it has only one connection to somewhere and it doesn't fall into the shortest paths of many other towns, you will rarely see anyone passing through your town, delivering messages. So this is the idea with betweenness centrality. It looks if your node is between a lot of basically, it is on the shortest path between a lot of pairs of nodes in that graph, excluding that node itself. So we'll formulate this as we first define an indicator function. For node K, this indicator function is 1 if it falls on the shortest path between I and J. It is 0 if K doesn't fall on the shortest path between I and J. And we say that it is sum over all starting points and ending points in our graph. We basically sum this indicator function, and that is going to give us our betweenness centrality. So again, it is, if your town is seeing a lot of messages go through your basically town, it shows that you have a lot of influence on that graph. If you are removed from that graph, it will affect the graph more, for example. So we have clustering coefficient, which is anti-centrality. It is a close concept to centrality. So a clustering coefficient looks at a node and its ego graph. And ego graph was the nodes that were directly connected to that node, and it basically the edges in between them. So it looks at the ego graph, for example, of node U, and see if its neighbors are connected to each other as well. So if the neighbors of U are neighbors of each other as well. And it finds the ratio of connected neighbors to the total number of pairs of neighbors that it has. So, for instance, here we have a total of one pair of nodes that are a neighbor of U, and we see that 0 of them are connected to each other, right? Therefore, it's going to be 0 over 1. So let's look at this graph again. We see that, so for example, for this guy, it has 1, 2, and 3 neighbors. Among these 3 neighbors, we have 3 pair of nodes, right? So we can have this pair of nodes, this pair of nodes, and these 2 pair of nodes. And so that's gonna be the denominator. Numerator is gonna be the number of neighbors that are connected. You see, one pair of neighbors are connected, 2 pairs of neighbors are connected. So it's 2/3, and it is gonna show 66% essentially. Again, you look at the denominator, you see that it has 2 roots, du equal to 0 and du equal to 1. So if any of these happens, this CU is not going to be well defined. So by convention, we say that if a node is disconnected, its CU is going to be 0. So a disconnected node over here, which is a part of the graph and it doesn't have any edges, its importance is 0. And we also have the same for the node that is basically only having 1 neighbor. So this node has 1 neighbor. This is going to be 0. It's not going to be well defined. By convention. We set this to 0. Now, if we looked at this node, we saw that 2 out of 3 pairs of nodes in this neighborhood are connected to each other, and that gave us a 66% centrality. If we also had an edge between the other basically pair of nodes, we would have had 100% or 1 as centrality. And if we look at that, it means that it is a subgraph of the graph where all the nodes in that subgraph are connected to each other. And that's the definition for a clique. So if we have our clustering coefficient equal to 1, it means that that ego graph of that node is a clique. Now we looked at the basically this clustering coefficient, and a concept close to this is called structural hole. If 2 nodes that are your neighbor are not connected, that missed link will introduce structural hole into your problem. So let's look at this node, which has a lot of neighbors, but 1, 2, 3, 4, 5, 6 neighbors. And out of these 6 neighbors, only 2 of them are connected to each other. And we have missed links all over the place. I'm just showing 5 of them. So these missed links introduce structural holes. Structural holes are basically can be a good thing or bad thing. So let's say that this is some town. And let's say that, this is a person, and these are his friends. So because his basically friends are not connected to each other, it means that this guy has control over the flow of information between different members of that society. So it's an important, basically, thing for that node. So let's say that previously we had, in old times we had Silk Roads, and some towns were just a hub that, there were no other routes around them, and you had to go through that road, basically, town, and they could have, they had more influence over the essentially transportation system. They were more prosperous and so on and so forth. At the same time, it can have negative, basically, effects as well. The negative effects for this are, if, for example, let's say that it is the road connection, basically street connections in a town. Let's say that there is some maintenance in this road. Now, structural holes means that there is not many alternative routes to take in this basically town. Since there's a maintenance here, we can't get out of this place basically in any way.